last time we have seen, uh, we learned about the stability classes in the atmosphere and how that will affect actually um, the dispersion of pollutant, right, from a stack. So for that, we generally use a Gaussian plume model, and that model says that there is no diffusion in x direction, but in y and z direction, the distribution of pollutant follow the normal distribution, or you can say Gaussian distribution. And according to that, the formula for concentration of any pollutant at distance x from the stack uh, in y and z direction um, uh, is given. And now, in order to calculate the concentration, uh, there is there are two, you can say sigma or s, whatever, means both terms are right. Standard deviation in y and z direction have been given through the formula, as well as the plots are available. Okay, so for a given stability class at a given downwind distance, the sigma x and sigma y can be seen either from a graph or can be calculated using the formula. And the stack height, which will be the physical height of the stack, and the plume rise. If you add these two, it will give the effective height, and that effective height will depend upon, especially the rise of the plume will depend upon the velocity, the wind velocity. If the wind velocity in horizontal direction is high, very high, then the plume will bend, you can say, easily, and the rise will be low. The plume rise will be low, because the horizontal velocity will try to bend the plume towards the ground. So all these fundamentals we have learned, and now we need to see one situation, which is the worst situation, if there is a inversion, which happens during the winter season, generally during the winter season. And the reason for inversion is inversion, which is thermal inversion, because the ground, or the surface of the earth remains warmer than the upper atmosphere sometimes. And like but the temperature, the whole temperature lapse rate changes. So temperature at the ground will become low, and the temperature at various altitude would be higher. So this is just opposite to the normal phenomena, uh, where we consider that the temperature at ground would be higher, and the temperature will decrease with height. But in some cases during winter, it's the opposite. Okay, in those cases, what will happen? So if this, you can see the figure on the left hand side, where t on x-axis and z, which is altitude, on y-axis is given, and the temperature near the ground was normal and the lapse rate was normal. However, there is a opposite temperature trend above a certain height L. So in that case, what will happen? The atmosphere near the ground, which is the lower atmosphere, will be unstable. However, the atmosphere above this L distance, okay, or L height from the ground, will become very stable, right? Because the temperature is increasing with height, right? That means the surrounding temperature will be, you can say, uh, higher than the temperature of the air parcel. In that case, air parcel will be heavier and it will not go up. So this kind of situation, when this kind of situation happens, what would be the direction of the, what would be the distance the plume will stop rising up in the atmosphere, and it will, even the dispersion or dilution will happen in the downward direction. Okay, this is what this figure is showing. So say it is XL is the distance where the plume will touch the base of the inversion layer. So at L height from the ground, the base of the inversion layer exists, and above that the temperature or the thermal gradient is opposite. Now at this point where at XL distance, the plume will start, because the atmosphere below this inversion layer is unstable. So the plume will start coming down, and it will be diluted by the atmosphere below the inversion layer. So, and at a certain point, say 2XL, this is it's a empirical formula, means it's based on the observation. At certain point 2XL, probably the plume will touch the ground. So that is the maximum distance given by the empirical formula. So this all the fact which I have just talked about is written here. Now in that case, what will happen? Sz can be given by this particular formula, and the concentration at distance 2XL can be given by the formula written on the bottom of the figure. Okay, so these you can if you are interested, you can derive this formula using the Gaussian plume equation, but it's not necessary in your it's like out of scope of your this subject. It is not necessary, but if you are interested, you can do it. Okay, now this is the problem related to inversion, and this is very simple problem. It says that determine the distance downwind from the stack at which we must switch to the inversion form of the dispersion model given the following meteorological conditions. So 2XL you need to determine. No, not 2XL, right? Inversion model will be applied. Okay, concentration can be of like using the inversion model can be calculated after 2XL distance. So 2XL you need to calculate. So okay, so I have done already. I have solved this question over here. See the solution. If you have any doubt or any question regarding this, we can discuss in the next class. Now, knowing this, we can now understand what would be the plume behavior, like plume which is coming out from the stack. How will it transport in the atmosphere depending upon the stability of the atmosphere, right? So you can see there are 6 cases written. Hello? Case A, say if the inversion, no, not inversion, the temperature lapse rate, which is solid line, is very sharp, okay, it's very high compared to environmental lapse rate, then what will happen in that case? There are like more turbulence. It's a completely unstable atmosphere, very high turbulence in the atmosphere. So plume will follow the looping kind of you can say path, because there is a turbulence. It will go down and up because of the vertical wind velocity as well as horizontal wind velocity. They are working together, so it will quickly move towards or downwind direction, as well as it will mix with the atmosphere. Now, if the temperature lapse rate is weak, right? It's not that that sharp, then what will happen? Because there is a like little stability in the atmosphere, the plume will come out. It may go in a horizontal direction, but dispersion will be limited. Okay, this situation is known as coning. Then if there is an inversion, then plume will not at all disperse in any direction. It will just go in horizontal direction depending upon the wind speed, and which we expect that during inversion condition even horizontal wind speed will be low. So it will move towards like in downwind direction in X direction. However, there is almost no negligible dispersion and dilution in the atmosphere. Now there might be the condition. See, this is all ideal assumption. There might be conditions. Two kind of situation may happen. One is altitude wise temperature lapse rate are different after a certain height. Okay, one thing. Second thing, the temperature lapse rate at one position at x1 would be different than x2. That may also happen. Okay, so D is the situation when altitude wise the temperature lapse rate is changing. So in case D, near the ground there is an inversion, while above a certain height, whatever, let's say L1 or whatever, there is a sharp, you can say, lapse rate, temperature lapse rate. That means the atmosphere near the ground is stable, while the atmosphere above this height L is highly unstable. So what will happen? The plume will cease to come down, but there would be enough dilution and dispersion in the upward direction. Okay, so this is known as lofting. Okay, so plume is going up. Now the another case E.
Ma'am,
Yeah,
will you please explain again how we decide where the temperature, where the atmosphere is unstable and where it is stable by
okay.
deciding the slope?
Yeah. So whenever there is a inversion, thermal inversion means the lapse rate is in opposite direction. Means there is a low temperature at ground and temperature is increasing with height, which is inversion situation. Whenever there is an inversion situation, there would be stable atmosphere. Okay, and whenever there is a normal lapse rate or strong lapse rate, means high temperature at certain point and the temperature decreases with height, then it is a unstable condition. And why it's a stable and unstable, we have already learned in previous class. I will just show you the graph which can explain it very well. Yeah, so just go through these two slides. Here I have explained why there is a stable and unstable condition based on the environmental lapse rate and lapse rate of dry adiabatic parcel and wet adiabatic parcel. Okay, moist adiabatic parcel. So so for the if what I have explained, I will just say in few words that uh, whenever there is a normal lapse rate, if it's a strong lapse rate, then dispersion and dilution, the condition will be highly unstable atmospheric condition. So turbulence would be there in the atmosphere, and therefore there is a high chance of dispersion and dilution of the plume in the atmosphere, which is this part. Can you see my pointer? Is that pointer visible?
Yes, ma'am.
Ah, when there is a opposite direction or lapse rate in opposite direction, which is inversion, then the atmosphere will be stable. There is not much turbulence, or you can say even no turbulence at all in the atmosphere. It's a calm condition, and therefore there will be no mixing in that direction. So now is that clear?
Yes, ma'am.
Okay. So similarly in E, you can see there is a strong lapse rate, normal lapse rate near the ground. However, there is a strong inversion after a certain height. Okay. So what will happen? Because there is a lapse rate near the ground, a strong lapse rate, uh, the turbulence would be there, and therefore the plume will try to like come towards the ground, and it will be dispersed and diluted in this layer. However, at the after a certain height L, because of the inversion, the further you can say the dispersion of the plume will cease in the upward direction. So this is how you can think of like stability and instability are linked with like strong temperature lapse rate, normal temperature lapse rate, and the inversion lapse rate or temperature lapse rate during inversion. So if it's a strong temperature lapse rate, normal one, then there is a instability in the atmosphere. If it's an inversion condition, then there is a stability in the atmosphere. So these are the slides which show and which explains further about the looping, coning, etc. And you can go through this, and it's a um, just it's good to means it will explain you more about this. However, I have tried to explain all the points. Now, these are some basic problems. See, in air pollution, uh, the fundamental regarding the gas pressure, temperature can be used in some of the problems, and therefore I would encourage you to, because these are the fundamentals you might have learned in class 12 or maybe in first or second year of your graduation detail. So I'm not actually going through this problem. You can see this problem and you can try to solve it and be prepared with this kind of problems. It may be a part of your like big numerical, or maybe sometimes this fundamental will be used. So that is what I want to say. Now today we will start the uh, air pollution control technology. So this slide I will upload, okay, today, and you can go through this. Let's see, where is my other slides? Yeah. Can you see my PPT?
We can see your screen,
No,
but
ma'am.
not PPT.
Yeah.
Now,
Now
now
it's
can
You
fine.
you?
see.
Okay, okay, fine. So after learning about the air pollution, the effect of air pollutants, uh, how they behave in the atmosphere once they are coming out from any pollution source, I would say there are much more to learn about this thing, but I don't want to go in like very detail, because this is not only the class for air pollution. We have to cover the water, wastewater, probably solid waste also. Let's see how much time we will have. I will cover the solid waste. Otherwise, I will just limit the whole discussion on air pollution, water, and wastewater, three area. So uh, after learning how much air pollution is deteriorating for environment and human health, we need to know, are there any control technologies available for controlling the emissions at the source only, means before it comes out in the atmosphere. So there are, like you can say, many technologies available nowadays, and one of the recent uh, advancement in this area is use of electrostatic precipitator for removal of very fine particles. So I means electrostatic precipitator is a device where electric charges are used to charge the particles and collect the particle on oppositely charged plates. So it's a simple phenomena. It was developed by Walker and Hutchings, and it was installed in 1885 in a lead smelter, but it failed because of some reason. Means it was not efficient to remove the particle. Probably lead smelter and all, they have a particle of very fine diameter, and also probably the charge provided to the plates will not be enough to charge the particle. So just I will tell you in one sentence that um, no, smaller the size of particle, larger the voltage required to charge the particle. Okay, so if particle is a small, high voltage is required. If particles are larger in size, like low voltage would be enough to charge the particle. So the whole principle was again developed by Frederick Cottrell, and it was applied or it was used commercially in 1906. And this is one of the most common device used in thermal power plants for collection of large size particle, because thermal power plant where coal is burned, there are uh, relatively large number of um, um, big particles, say greater than 1 micrometer, can be seen, and those particles can be removed effectively using the electrostatic precipitator. In this particle, mainly some ash particle, which are much more larger than the anthropogenic, the particles coming out from combustion of volatile species in coal. Uh, See, so when carbon fuel, any fuel which contains carbon, hydrogen, oxygen, if that kind of fuel is burned, uh, if there is a sufficient oxygen available stoichiometrically to burn the whole fuel completely and convert all the carbon to CO2, then that a particulate may not form. However, it's very difficult to have such kind of air to fuel ratio which can accomplish the complete burning of fuel. So there are possibility of having some of the carbon converted to, to be removed as VOC. Some carbon would be removed as black soot, and some carbon will remain in the ash. So the ash particles also come out from this thermal power plant, and they can be effectively collected using ESP. Now, ESP, what is ESP? ESP consists of the plate, corrugated plate, and the wire. And these plate and wire are charged with opposite charges using the electric field, which can have a potential of 30 to 75 kilovolt. And once this plates and mesh is charged, there would be some electrical field in between, which will produce ions. Okay, so when the gas passes between this mesh and the plate, the particles the ion will be attached, or will be a, they will get attached with the particle, and they will make the particle surface negatively charged or positively charged. But generally the charging is such a way that the particle gets negative charge. Once the particle will have negative charge, they will be attracted towards the positive plate, and they get deposited on the plate. So this is the simple mechanism. The working principle is shown very clearly here. So first step is charging of the particle. Second is, because the particle will have negative charge, they will be transported towards the positive charge plate, and then they will be neutralized because of the opposite charge on the plate, and then they can be removed using some kind of scrapping system, and the dust can be collected in the hopper, um, on the base of the ESP, attached on the base of the ESP. Okay, now this is the advantage and disadvantage. High removal efficiency of fine particles, but fine means here not less than 1 micrometer. Fine particles means here like less than 10 micrometer aerodynamic diameter, and even less than 2.5 micrometer aerodynamic diameter, but the lower limit is 1 micrometer or above. Handling of large gas volume with low pressure drop. Okay, large gas volume can be handled without much pressure drop. Collection of either dry powder material or wet fumes or mist. Okay, so dry powder material, or if the flue gas is dry, it doesn't have much moisture, then this is an effective device. Otherwise, there would be a chance of corrosion. Sustain a wide range of gas temperature up to even 700 degrees centigrade, low operating cost except at very high removal. So if you want to increase the removal efficiency, then probably the cost will increase, because the voltage, you need to increase the voltage. There might be some other, we will see one problem related to this also. So disadvantage: high capital cost, unable to collect gaseous pollutant, so you cannot collect the gaseous pollutant. Large space requirement. Okay, it's a big unit, very big unit. Variation of removal efficiency with particle or droplet properties, such as resistivity of the particle or droplet. So that is something, disadvantage here. Now, so here the ESP efficiency can be given by this empirical formula. The eta is equal to 1 minus exp A into W upon QG, where A is the collection area of the plate, W is the migration velocity of the particle. So migration velocity of the particle will depend upon the charge on the particle, and it's given here, right? There are two formula given here. QG is the gas flow. Okay, let me use the pointer. Okay, so W, migration velocity of the particle in meter per second. There are two formula given here. It will depend upon the charge. Then QG is gas flow rate. Then like corona power requirement of ESP, PC can be given by this. Where what is PC? Because W depends upon PC, so the formula for PC is given here. These are very small formula, because you will have open book exam. You don't have to mug up the formula. You can use the formula directly from this slide. Okay, so okay, one thing we need to understand regarding the particles. What happens for very small particles less than 1 micrometer in aerodynamic diameter? Even means I think it's applicable for even a smaller particle. That See, I did not teach you the aerosol technology, but I will try to explain it here. that what will happen if there is a few particles in the atmosphere or in the flue gas, and there is a large number of gas molecule, right? And these gas molecules are 2 to 4 nanometer in diameter, but they are numerous in number, while the particles are 10 nanometer or 5 nanometer to 100 micrometer, right? And they are fewer in number. So what will happen? Uh, this gas molecule, because they have random motion because of their kinetic energy, and with the increase in temperature the kinetic energy increases, and they have a random motion according to ideal gas law. Their even collision of this gas molecule is very like perfectly elastic. They collide with each other and then they go in the opposite direction in linear path, with the same, like the velocity in x direction and minus x direction will be of same amount. Therefore their total velocity inside a container would be on an average zero. This is what we say, and that's why we say the gas inside any container is stationary. So now you know, like, and you know that the gas molecule will not only bombard on whatever surface they have if they are inside the container. The similar phenomena will also be imagined on particle surface. So if the particle is there which is heavier than the gas molecule, and the gas molecule have bombardment over the surface of the particle, there is a possibility that the the trajectory or the velocity trajectory, you can say, the movement of the particle will be affected by the bombardment of these gas molecules. And in order to account for, especially for a very small particle, as I said, 1 micrometer or low, in order to account for this phenomena, which is the you can say effect of gas molecule on aerosol or particle, there is one correction factor. Cunningham correction factor was introduced by scientist Cunningham, and that depends upon the particle diameter and the temperature of the gas, the flue gas. So this correction factor needs to be applied when we calculate the settling velocity of the particle, or or any other parameters or characteristics related to the particle. So here, for migration velocity of the particle, the C is applied in this formula, okay, for a small particle. Then eta can also be given by this particular formula if Pc is given, right? So there are two formula of efficiency. One depends upon A into A and W. The second will depend upon Pc and Qg. So this formula you can see from your slide when you will solve the problem. So here one problem I
Ma'am,
have. Yes.
ma'am, how we are defining efficiency here?
Efficiency is how like percentage of particle removed from the total particles in the gas stream.
And ma'am, what is corona power or corona current here?
Okay, Corona power. See, I don't have the definition right now, but I will tell you in the next class. It's not a problem. I removed some of the slide related to this. This I thought like it's not required for you to learn. It's like more complicated formula are there. We will discuss that sometime. But yeah, I will next class. I will definitely tell you what is the Corona power. Okay. So this is these are the problems. You can go through the problem. One homework I have listed here. So application of ESP. The ESP can be applied in electric power industry, means that is power generation, thermal power plants, etc. Pulp and paper industry, metallurgical industry, cement industry, etc. Okay. Can you mute your Microphone. Use your microphone. Okay. The other device is very simple device which has just a fabric or cloth kind of material which is used to filter the flue gas, filter the polluted gas. Okay, and there are two kind of filters. One is deep filter, another is bag house filter. Deep filters are, you can see on the left hand side, one of the picture of deep filter, and these are generally used in air conditioner for very, you can say, less contaminated gas if the particle concentration is low. However, bag house filter, which is on right side, are used in industries where these bag houses are is like parallelly or can be used in parallel or in series, and you can see the many bag houses are assembled in one unit, and the gas this is the direction of dusty gas. You can see this is the direction of dusty gas. When the gas goes in, it will it will go up, and it will like the particle will remain inside the bag house, and the clean gas will come out. So this is simple filtration kind of mechanism. However, there are uh, four or five different mechanisms we can visualize, or we can, you can say, we can think of. See, once because this bag house filter are the fabric is having some kind of fibrous structure, right? So there is a chance of interception. Interception means what? Once the particle is there, uh, it will be intercepted, or it will be even if there is not much you can say velocity in of the particle. It's say it's very small particle, its mass or inertia is not enough, and though it is going through that filter bag, it's a chance that there is a Brownian motion of this particle. So its gravity its mass is very low, so gravitational force or whatever force you have applied is not enough to drag or to change the you can say the path or trajectory of the particle. So that kind of particle will just impact, will just intercepted by the fibers, and it will get attached to the fiber, and it will be removed. There is another mechanism which is impaction. So the particle will be, means it has enough inertia or enough mass, so it will impact on the fiber, and it will be removed. So there are two three different mechanisms other than sieving, but major mechanism in this large bag house filter is sieving. Okay, so high efficiency control of particle less than 5 micrometers. Okay, so this is good for a small size particle. Two types, deep bed filter and bag house, I already told you. So now bag house filter, we can see that sieving is the fundamental mechanism of particle removal, interception of and electrostatic attraction could be there in removal of the particle. Difficult to capture a small particle, very small particle, which is again less than 1 micrometer in aerodynamic diameter. Natural or synthetic fiber. So there are two type of fiber. Synthetic fibers are more common because of their chemical resistance. So bag house filter life is 1 to 5 years. Bag house diameter could vary from zero point 0.1 to 0.35 meter, means 35 centimeter, and length 2 to 10 meter. So it's very large bags. Okay. Cotton and wool fiber bags cannot be used for temperature above 90 to 100 degrees centigrade. Glass fiber can sustain temperature up to 260 degrees. So it depends upon the material, what kind of material is being used. Um, uh, According to the temperature of the flue gas which is coming out from the stack or from tailpipe of the vehicle or whatever. So it all depends upon the temperature of the flue gas and the collection efficiency we need to clean the air. So accordingly, we can decide on which type of control device we want to use. Liquid scrubbing. So what will happen? The baghouse filter is good for, you can say, dry gases. Sometimes baghouse filter is also combined with weight uh, weight process, which means in order to remove the gases, NOx and SOx from the flue gas. Sometimes weight treatment, which is like pouring the or sprinkling the water jet on flue gas, is also combined with baghouse filter. So the sulfur dioxide and nitrogen oxide can also be removed, or you can use the liquid scrubbing system for such application. When the particulate matter to be collected is weight corrosive and very hot, the weight scrubber are used. So weight scrubbers are not only remove the weight particle, if there is a like high moisture content of the flue gas, um, this weight scrubbers are good, but they are also efficient in removing the gases, sulfur dioxide, nitrogen dioxide or nitrogen oxide, by converting them to HNO3, H2SO4, etc. Application in emission of talc dust, phosphoric acid, maize, foundry. So these are the application of liquid scrubbing. Simple spray chamber are used for coarse size particle. Okay, so high efficiency removal of fine particle. The combination of Venturi scrubber followed by cyclone. So what happens? You can have a Venturi or weight scrubber over here, and you can remove the weight particle or remove the particle by attaching the particle with the liquid droplets. Uh, this will also remove the sulfur dioxide, nitrogen oxide, etc. by converting them to sulfate and nitrate droplets. Then after that, the cyclone can be connected, where the dry particle of smaller size can be removed with different mechanisms. We will learn about the cyclone separators also. So this is how it works. Um, Okay, so here the differential velocity between the droplets of collecting liquid and the particulate allow the particles to impinge on the droplets. So as I said, the particles will be actually attached to the liquid droplet. Since the droplet, since the droplet particle combination is still suspended in the gas stream and inertial collection device is placed downstream. Yeah. So this is what, if the droplet is big enough, it will be deposited or removed in the Venturi scrubber portion, or when it passes through the throat. However, if the particles are very small and the weight of the droplet is not enough to get settled, then the cyclone will help in removing those kind of particles. Okay, so this is how it works. So here again, the efficiency of the liquid scrubber can be given by this formula, where the kappa is correlation coefficient gas per meter cube of liquid. So how much um, uh, gas, flue gas, you can say, volume per meter cube of liquid, or 1 meter cube of liquid. That is the correlation coefficient, or the liquid flow rate, meter cube of gas per meter cube of air. Okay, liquid flow rate. It's a meter cube of liquid per meter cube of gas. Okay, liquid flow rate. Psi is inertial impaction parameter. which can be given by, again, C is coming here, which is Cunningham factor. Rho P is the particle density, Vg is the speed of the gas at the throat, dP is particle diameter, dd is the diameter, droplet diameter, mu is the viscosity, dynamic viscosity of the gas. Okay, not liquid, it's a dynamic viscosity of the gas. So can you see, like, this formula is similar to one of the very common formula. Can you tell me what is that? Do you remember Stokes law? What is the formula in case of the Stokes law?
Uh, Force is equal to 6 pi eta RV
Or it can be changed to 1 by 18 of what?
by
So
uh,
just see the Stokes formula. It would be 1 by 18, would be same as here, and this portion will change. One minute, I will again go for pointer option. So 1 by 18 will be there. Even Cunningham factor will be there for small particles if we are talking about the particle, and then this will be different. Mu will be there. Mu will be there in Stokes law, but there would be some changes in the numerator. So you can go through that. Vg can be given by Qg upon At, where Qg is the gas flow rate, say in meter cube, At is the cross-sectional area of the throat. So A is the cross-sectional area of this throat, okay, venturi throat, okay. So maybe it's a multiplication of this width multiplied by height of this throat, okay. Here, the one of the problem is given. The problem says the details of the scrubber is given below. Determine the efficiency of the Venturi scrubber. Assume the particle are fly ash with the density of 700 kg per meter cube and minimum size of 10 micrometer. Okay. So all the particles are greater than 10 micrometer in size. Throat area is given as 1 meter square. Gas flow rate is given as 94.4 meter cube per second. Gas temperature is given. Liquid flow rate is given as 0.13 meter cube per second. Coefficient kappa is given as 200. Okay. And droplet diameter 100 micrometer. Gas viscosity is given as 25.2 into 10 raised to 6 Pascal. So it's a direct application of the formula. So cyclone is another unit. I think we will learn about the cyclone, and I would like to have some more, you can say, numerical related to ASP and liquid scrubber. Maybe next time, and then we will come to cyclone. So next time we will learn more about the ASP and liquid scrubber, and then next class we will have the cyclone. Okay. So 2 or 3 devices are remaining: adsorption, cyclone. Yeah, 2 devices. Yeah, and this is again, this is chemical method. Okay. So is there any question? Any question related to? So I would.
there was a slide. Excuse me, ma'am.
Uh-huh.
There was a slide of ASP where it was written that it in the advantages list it was written that it makes a low pressure zone or something like that.
1 minute. Yes.
Yes, ma'am. Handling of second point, handling of large
Yeah.
gas
No
volume with low
pressure drop.
pressure.
No pressure drop.
Uh,
No pressure drop means.
what,
Pressure drop means, see, the distance between this plate and the mesh. Um, Once the particle is deposited on the plate, right, the distance will reduce, right? Right? The distance between mesh and plate will reduce with the layer of the particles building on the plate. right?
Okay.
Right. So what will happen when you are supplying the gas between this mesh and the plate? There would be the increase in pressure between this with the deposition of the dust layer on the plate, right?
Okay. Okay.
But this pressure drop is lower, means it's low compared to, means it will not affect the efficiency of the ESP until it's a worse condition where this blockage or the layer becomes so thick that the gas cannot pass through between the mesh and the plate. Okay, so with the building up of this dust layer on ESP plate, the gas flow will be restricted. But because it's a large unit, right, and the distance between mesh and plate is relatively enough, the pressure drop will increase slowly, but it will not go beyond the certain limit where gas flow is very or restricted, right, beyond a limit. Okay, so this means it can handle the large volume of gas, very large volume of flue gases with high contamination at low pressure drop. So pressure drop means the pressure at the inlet where gas is entering the system and pressure at the outlet where it is going out from the system, right? So this pressure drop between this 2 point inlet and outlet will be low, even lower. You can say lower compared to the other units. For example, in case of, let me see, in case of bag house filter, as we know, this is the sieving mechanism. So what is happening? There are the pores in the filter or in the fabric. So once the gas will pass through this fabric filter, the particle will be deposited on the fibers of the filter, as well as they will try to clog the pores also, right? So the pressure drop on the one side of the filter and the clean gas which is going out, the pressure drop will increase, right? Because of the clogging of the filter, right? Is that
Right.
that yeah? So
Yes, ma'am.
that kind of thing cannot happen in ESP because ESP has like large area. There is a sufficient distance between the mesh and the plate. Even though there is a formation of dust layer on the plate, the pressure drop it can handle the pressure drop or pressure large volume of gases with low pressure drop. The pressure drop will be lower. Now is that clear?
Yes, ma'am. Yes, ma'am.
Yeah.
Makes sense.
Yeah. What else?
Can we leave? We have other classes at 9.
Okay, you can leave. So if there is no other question, we will learn about ESP and this thing, the backhouse filter next time. Okay. Thank you.
Excuse me, ma'am.
Yes.
Ma'am, can you tell where are the lecture slides uploaded?
On
It
MS
is
Team, I am uploading under class material.
it is in file
Ma'am,
inside files in class notebook.
Yeah. So
in the
I will tell you. There is a file,
okay.
and inside the file there is a class material. Let me just share it once again. Can you? Okay. Where is that? Yeah. Can you see my screen now?
Yes, ma'am.
Yes, ma'am.
So here all the three PPTs are there. Okay. So go to files and in files there is a class material. So here I am uploading the PPT. I will upload even your you can say attendance related means percentage attendance after minor one in this section only. So everything will be uploaded in this section.
Okay,
Right?
ma'am. Thank you.
Thank you.
Okay.